My name is Tong Qingyu.
My name is Zhezhou Zhang.
My name is Pengyu Zhang.
We are all majored in electrical engineering. Let's begin our presentation.
Our project is implementation of two-level on-chip caching and the study of the effect of various parameters. The project is based on simple scalar under the Linux environment. Basically, average memory access time can be used to measure the performance of cache. So in this project, we will use miss rate, which is a main parameter that affects the performance of cache. We will keep changing three parameters: block size, associativity, cache size, to see how miss rate is going to change. The simulation tools we used in this project is SimCache and SimCheetah. These tools can help us set the configurations of each level of cache. And in this project, we only use one benchmark to test the output, which is test mass. We will use some other test bench in the further study. The methods we are going to use is control values. So we fix two parameters each time and changing the other parameter to get the value of mass rate. Here is how SimCache works. We set the configuration of level 1 cache and keep changing the parameters of level 2 cache, such as number of sets, block size, and associativity. In this example, the level 1 instruction cache would be 32 sets, 16 bytes block size, one-way associativity, and use the least recently used replacement policy. And from the list of output, we should find the miss rate of level 2 instruction cache. In SimCheetah, the value is set based on the log of 2. So L5 means 5 to the power of 2, which is 32 bytes cache lines. The generated output is an example to see how sets and weights can affect the miss rate. Here is how we accomplish this project. In this flowchart, we measure the miss rate of level 2 cache when the level 1 cache is fixed. Different color represents different parameter, which is also applied in the later slides. These two figures are based on the simulation results. For example, the level 1 cache is 32 sets, 8 bytes block size, one way, least recently used, and we show how block size and cache sets can affect the miss rate of one-way level 2 cache. The lines in different color represents the different block size we set with respect to the number of sets, from 32 to 1024. We can see the trend that miss rate decreases when we have larger block size and more cache sets. In next two figures, we compare the miss rate between one-way and two-way cache. Since all the parameters remain the same, the two-way means a larger cache size, which can cause lower miss rate. The rest of figures stand for the other combinations of the three parameters. All of them show a result of how these parameters influence the miss rate. We will have a quick look at them and skip to the conclusion. So from the simulation results, we can know larger block size can reduce the miss rate. Higher associativity can reduce the miss rate, and larger cache size can reduce the miss rate. The reason why larger block size can reduce compulsory misses is because the larger block size can take maximum advantage of spatial locality. But if blocks are too large, there are fewer blocks available in the cache, which can cause more potential conflict misses. Highly associative cache can have a lower miss rate. Each set has more blocks, so there's less chance of a conflict between two addresses. Overall, this will reduce average memory access time and memory store cycles. Larger cache sets can lead to larger cache size. Cache size also has a significant impact on performance. In a larger cache, there's less chance there will be a conflict. Again, means the miss rate decreases, so the average memory access time and the number of memory store cycles should also decrease. Here is how we're going to do the further improvement of our project. We will use two more benchmarks to get the different simulation results. The benchmark can be still in the simple scalar, such as anagram. Also, we can use some other benchmarks tools from other sources, such as SpecSPU 2000. Furthermore, we should come up with a cost-effective method to choose the configuration of cache. We can limit the miss rate by using high-tech multi-level caches, but it will lead to the much larger cost in relative to the performance it can give. So according to the problem, we can see how the value of parameter is going to meet the demands. For example, which cache size can be more appropriate for the current market. The topic of our project is significant to understand the two-level cache design and the impact of different parameters with respect to the effectiveness of cache. Most parts of the proposal are finished in the presentation, and we will try to finish further improvement. Also, the link of simple scalar is down in the description of the video. Thank you. That would be all.